the topic pyramids. The next important topic in computer vision is pyramids and wavelets. So now we'll see about the pyramids. Pyramids is a collection of images. So we know the pyramid image representation, right? How the pyramid will look. It will be of triangle shape. So it is nothing but the collection of images is known as image pyramids. How this collection of images are formed means a single image will be reduced in size, reduced in size, reduced in size, and finally it forms a triangle shape, that is pyramid. So we have to decrease the size of original image in order to get a pyramid. And if you want to reconstruct the original image means I will perform upsampling. So this is known as downsampling as well as upsampling. Okay, the original image is downsampled to form a pyramid. If I want to reconstruct means from the top I'll enlarge to the last one, so that is known as upsampling, which is the same version of the original image. And each level of the image represents the different scales. Okay, so downsampling means we will this is very important. The upsample and downsample will see in the entire portion. So downsample means we will reduce the size of image by decreasing the number of pixels. Already it has certain number of pixels. We will decrease that. We will decrease the number of pixels. The concept we will see in downsampling is decimation. And the vice versa of downsample is upsample. Upsample means we will increase the size of the image by increasing the number of pixels. The concept we will see for upsampling is interpolation. Downsampling is also known as decimation. Upsampling is also known as interpolation. Okay, so how we will upsample means we will insert the zeros to enlarge the images. So each level represents the different images. So types of pyramids are Gaussian pyramid and Laplacian pyramid. This will also be covered in the upcoming slide. So Gaussian pyramid means each level is created by smoothing and downsampling. It is useful for analysis and compression. Laplacian pyramids means it is the extended version of Gaussian pyramid. It will store only the difference. It may be useful for reconstruction of the image, blending and compression. Okay, so that's what represented. Why we need image pyramids means it can be useful for object detections, or it may be useful for multi-scale image editing. So it can be useful for object search. That's what mentioned here. So next one is interpolation. So as I said earlier, the interpolation means upsampling. So it is the process of estimating unknown pixels when resizing the image to higher resolution. Upsize means we will convert the normal image to higher resolution, right? So we will increase the image. In order to change the normal to higher, we have to find some unknown values. That is interpolation. Interpolation is the process of estimating unknown pixel values when resizing the image to the higher resolution. So we have interpolation kernel. The formula is mentioned here. G of ik equal to summation of k comma l f of kl, h of I minus rk, and j minus rlk. So this f of k comma l represents original image pixel. Okay, original image pixel. If an image is having collection of pixel, this original image pixel is represented as k comma l, and g of I j represents the upsampled one. On applying this kernel, we will get a resultant image, right? Enhanced one or enlarged one, that is represented as I comma j. So h represents the interpolation kernel, the kernel which is used to convert the original to upsampled one, and r is nothing but upsampled factor. Upsampled factor is nothing but a value. It can be 2 or 3. So we'll see an example also. So this is the interpolation kernel. We will use the same for decimation also. I'll tell that. And the next one, we have two figures, the figure A and figure B. Figure A represents the weighted summation of the input values, and the B represents the polyphase filter representation. In A, the input samples are f of k, f of k minus 1, and f of k plus 1. Because in previous case we have considered the f as the input 1 and h is the kernel, right? So the f represents the original input and h represents the kernel. So h of I minus rk is convolved and produces the result as a red triangled one, G of I. So each input sample is multiplied with the interpolation kernel. So that is f of k into h of I minus rk. In this case, f of k plus 1 into h of I minus r of k plus 1. Okay. So here f of k minus 1 into h of I minus r of k minus 1. Okay. On performing the multiplication, we are getting the result, and that is represented as g of I. This is the interpolated one. Okay. The B figure represents the alternative view of the same process. Instead of each input sample is convolved with the interpolation kernel, a single kernel h of I minus rk is used. Here we have used every interpolation kernel, and we have multiplied every input convolved with we have every input convolved with the interpolation kernel and produces the result. So here I am going to use only one interpolation kernel, that is represent the red curve. On multiplying these values with a single kernel, I am getting the result in the green color one. So this is the polyphase filter representation. Both represents the same process. Okay. So types of interpolation kernels are linear interpolator and cubic interpolator. And one more thing we have that I'll show in the next slide. So linear interpolator means it is a 10th kernel. Cubic interpolation means it is a smooth bell-like or Gaussian interpolation. So we have already in previous video we have seen about a 10th kernel. 10th kernel means the resultant would be of sharper edges, and in case of Gaussian means we won't have any sharp edges, it will be of smoothened one. So linear represents 10th and the cubic represents the Gaussian one. So we'll use these interpolation kernels to upsample the images. So here, yes, it is 1D, 1D. So in bilinear, bicubic. If I am going to use a linear kernel or cubic kernel means it represents the one dimension. Bilinear, bicubic represents two dimension. So linear interpolator in general it is 1D. Cubic interpolator in general it is 1D. So bilinear, bicubic means it is 2D. We have four images, that is a two-dimensional image interpolation. So on applying the linear interpolation, the image is enlarged. We have taken an original image. So what we are trying to say is we have taken an original image. On applying the interpolation, okay, on applying the interpolation we got so and so results. That is what represented in this figure. So on interpolation also we have seen linear as well as cubic, right? So A represents application of linear interpolation kernel and B represents bicubic, and C is also bicubic, and one more interpolation kernel is windowed sync, which is much better than linear and cubic. So now let's see the results. So the original image on applying the interpolation, it would be upsampled, right? The image will be increased. That is what we have seen in previous. So the A represents linear one, bicubic represents A equal to minus 1, and it is having a certain formula. I'll show that formula in upcoming slide too. So we'll have a factor called A. Based on A, the image value will be completely changed. So on applying A equal to 1, we have a certain image, and on applying A equal to minus 0.5, the image again it is shown here, and windowed sync. On comparing all these four images, we can observe that the windowed sync is much better. Okay, so you could see that linear, in case of linear, it will take only the four nearest neighbor pixels, so it will works on 2 cross 2. Bilinear works on 2 cross 2, and a cubic, sorry, y cubic, it works on 16 surrounding pixels. So 4 cross 4 produces 16 surrounding pixels. A equal to minus 1, it will prioritize the sharpness. On comparing A with B, some details are more sharper. You can see this part. Okay, so this is much sharper when compared to the bilinear one. So when A equal to minus 0.5, it prioritizes the smoothness. So when compared to bilinear, it is not that much sharp as well as it is not that much blur. So it prioritizes the smoothness. Windowed sync means it will consider large number of surrounding pixels. Okay, here it will take 16 pixels, here it will take 4 pixels. It will take large number of surrounding pixels to produce the result. So this results in extremely sharp result. Okay, the quality results will be more high when we use windowed sync, but it is more computationally expensive. That is what mentioned in the slide. So I said right, previously bicubic will be using a certain formula to interpret the result. That formula is mentioned here. H of x equal to so and so. Here this a factor is controlled the shape of the cubic plane. So yeah, bicubic interpolation means it is a 2D extension of the cubic convolution kernel. So graphics card uses bilinear kernel. Some photo editing packages uses the bicubic interpolation. So depends on the application, we can use bilinear interpolation kernel or bicubic interpolation kernel. So yeah, choice of A equal to minus 1, which results in more sharper result, but it may result in ringing artifacts. Ringing artifacts is nothing but this. If you take an image, on editing the image, you may have seen this type of result. So this is known as ringing artifacts. So it will provide a sharper result, but the drawback is that it may introduce ringing artifacts near the strong edges. So other common choices are A equal to minus 0.5. We can use minus 0.75 also. It will balance both ringing as well as blurring. Okay. So the next one is on applying the frequency domain. So we have already seen about the purpose of frequency domain in Fourier transform. The same what represented here. So here we have two images. So the first image represents the spatial domain and the second image represents the frequency domain. So the figure A, it represents spatial domain result, and the figure B represents Fourier transform result. Fourier transform or nothing but frequency representation. The Fourier transform is mainly used to convert the signal to the frequency domain, right? So look at the image A very carefully. So we have all the three kernels which was discussed earlier. We know, right? So tent is nothing but linear. The linear interpolation is named as tent, and the cubic interpolation with the two values A equal to minus 1, A equal to minus 0.5, and Windows Inc is one more interpolation kernel. So three types of interpolation kernel is mapped in the spatial domain. Spatial domains means a normal human view, and in case of frequency domains means it is the one which is suitable for processing the images. So on zooming it, you can see that the tent represents brown color and it is a very sharp edges, the flat one, and it is a sharp edge. So the cubic is somewhat smoother, it is a Gaussian, right? So somewhat smoother, but green color one somewhat smoother, and as well as pink color also. The blue is windowed sync, it is having some humped oscillation. Okay, it is having some humped oscillation, bumpy oscillations. So the figure b represents the conversion of the same windowed tent cubic into the frequency domain representation on applying Fourier transforms. So using this figure image B, we can understand which frequency details in an image are preserved, which frequency details in the image are suppressed. Okay, the frequencies are represented 0, 20, 40, 60 till 100. Okay, now see this. A is windowed sync. Windowed sync preserves the mid frequency to high frequency. Cubic is also somewhat like that, but the tent and cubic is not that much preserving the high frequencies. Okay, so high frequencies means it will produces the sharper result, but it results in ringing also. Low frequency means the result may have less ringing, but the blur may be more. So if you want sharper details, we have to go with high frequency. If you want less ringing, we have to go with low frequencies. Depending on the application, we can choose the type of the interpolation kernels. So it is just an introduction about the cubic spline. Spline is nothing but cubic B spline, right? So the spline is nothing but any piecewise polynomial function. The splines can be linear spline, quadratic spline, and cubic spline. So in this previous example, we are focusing on cubic spline only, and it is a commonly used for interpolation one. We are using cubic spline in interpolation, and it can be useful for computer aided design, and in computer vision we can use this spline to elastic image deformation, motion estimation, and image processing operation can be effectively carried out using this spline. Again, the windowed synced interpolation is one of the high quality interpolator, and due to this sharpness, it may introduce excessive ringing. Some may dislike that. So, some individual dislike the excessive ringing. On alternative, we can go with the repeated interpolation, or we can use bilateral filtering. So, these are just some of the uh, general theoretical part. Next, we are going to see about decimation. So far we have seen interpolation. So in the beginning I have said interpolation and decimation are the very important parts of pyramid. Interpolation means upsampling, decimation means downsampling. So interpolation increases the image resolution, while downsampling, decimation, it decreases the image resolution. And I hope you are remember the previous formula. So I have highlighted, right? So the same interpolation formula, but this interpolation kernel value will be changed. What we have seen here, g of ik equal to summation of kl, f of kl, h of I minus r, k and j minus rl, right? So f of kl is original image, g of ik is upsampled, h is the interpolation, r is the upsampled factor. So the same, but with some variation we are going to see here. So f of KL, again it represents the original image. Here G of Ij represents downsampled image, and H represents, there it represents the interpolation kernel. Here it represents the decimation kernel, also known as low pass kernel, low pass filter kernel. And R represents downsampled factor. How much we have to downsample? It is a numerical value, either 2 or 3 we can say. So this figure represents the decimation curve. Previously we have seen interpolation curve, right? So in case of interpolation curve, we have converted the weighted summation or polyphase. Similarly, we are going to see some curve for decimation too. So this is the original sample. On applying the decimation, the image B is shown here. Okay, look at here. The original samples are having certain waves, and on applying a low pass filter, the waves are reduced, and we have decimated this with the factor 2. Why 2 means? So see here, every second sample is preserved. Okay, so we are omitting this and we are preserving this, and we are downsampling 2 and we are preserving this. Again we are downsampling this too and we are preserving this. We are downsampling this too and preserving this. So only the tick mark parts are maintained here. So this and this is maintained. So if the downsampling factor is 3 means, we will skip the 3 values. We will skip the 3 ones, and the resultant would be the decimated one, which would be the reduced image. Okay, from the original image we are skipping some parts, so that would result in a reduced one. So yes, so we have seen a separate formula for interpolation as well as we have seen a separate formula for decimation. A smoothing kernel can be used for both interpolation as well as a decimation, that is mentioned here. So again, f of k is original value and g is upsampled or downsampled one. H is the kernel. Here it is a smoothing kernel. Previously we have said it is a interpolation kernel or decimation kernel. If you want to use the same kernel for both, we can use it as a decimation kernel, and it is having certain formula. So in case of interpolation, we will insert the empty cell to make it enlarged. In case of decimation, we will drop the cells in the image based on the R value to reduce. Okay, so we can use one more filter called as binomial filter as a decimator. So probably we'll use the decimator factor as 2. It can be used in applications like image blending, aliasing. Binomial filter can be used. Yes, in this slide, we are having certain filters that can be useful for decimations. So the linear filter downsample rate is 0.5, 0.25, and binomial 0.375, 0.2500, 0.25. So these are all some of the values we know. So linear means it is tent. We know, right? Tent means, so this value is A and B. So we will represent A, B. So 0.50, 0.25, 0.25. So this may look like a tent. Okay. So similarly, binomial also 0.375 is A, B, C. So how we will write A, B, C, B, C. So A value 0.37 would be in mid, 0.25, 0.0625. So here also 0.25, 0.0625. So similarly, all the values can be represented as a filter. Okay, so all these filters are summed to produce the value 1. Yes, so you can see the linear filter binomial, the result of the linear filter is much poor when compared to binomial filter. The binomial filter result would be less poor than cubic. So Windows Sync is having much better results. So similarly, QMF9, JPEG 2000, these are all the good quality filters used to preserve the details in well manner. Okay, the same values mentioned here, and the frequency response that of the two cross decimation filters. Two cross decimation means the downsampling factor is mentioned as 2. The frequency response is considered here. So I said earlier the last two would be resulting much better. So the curves are like this. So linear is very poor. You could see that the line is very flat. The linear is dark blue, right? So the line is very flat when compared to QF9 and JPEG 2000. Okay, so consider this two line alone. Sorry, consider this two line alone. This is very flat. There is a linear. The results are very poor. When compared to JPEG, it is much better. Okay, that's what mentioned. The next one is multi-resolution representation. So multi-resolution representation means the normal pyramid can speed up the course to find search algorithms, help to identify objects and patterns at various scales, and enabling the multi-resolution blending operations. So they find extensive use in computer graphics for fractional level decimation through MIP mapping in both hardware as well as a software. Okay, so here the last level is a fine level, mid level is a medium, and last one is core level. L equal to 0, L equal to 1, and L equal to 2. Okay, each level has half the resolution. Okay, here it is 8 cross 8, it is converted to 4 cross 4, and then it is converted to 2 cross 2. Okay, so half level, and then the last one is quarter level. Yes, the very important topic is Laplacian pyramid in case of multi-resolution representation. The Laplacian pyramid is derived from the Gaussian pyramid. Okay, so this is the very important point. Please make a note of it. So Laplacian pyramid is derived from Gaussian pyramid. So in case of Gaussian pyramid, we will do two steps. One is blur and then down sample. In case of Laplacian, we will upsample and then apply the blur. So these are the two important steps we must know. I'll discuss that in detail also. Yes. We need binomial kernel to do this operation. So let us see the binomial kernel proposed by Bert Adelson. So five type kernel. So C, B, A, B, C is the kernel shape. It is five type. So they are going to, we know summation of all this should be 1. So I am going to take A plus 2B plus 2C equal to 1. We are going to take B equal to 1 by 4. On taking B equal to 1 by 4, A plus 2B plus 2C equal to 1. So A plus 2 by 4 plus 2C will be 1. So A plus 1 by 2 plus 2C equal to 1. 2 A plus 2C equal to 1 minus 1 by 2. A plus 2C equal to 1 by 2. And 2C would be 1 by 2 minus A. On dividing this, C equal to 1 by 4 minus A by 2. The C formula is derived in such a way. And the value we are going to take is, already we have taken b equal to 1 by 4, and I'm going to take a equal to 3 by 8, which is 0.375. So on applying in this formula, I'm getting c equal to 1 by 4 minus 3 by 16. So it would be c equal to 1 by 16. The value is 0.0625. 3.8 is 0.375. So the value C is 0.0625, value A is 0.375, value B is 1 by 4, so it is 0.25. We have three values. So on applying this in a kernel format, what are the results you get? 0.0625, 0.375, sorry, 0.25 and 0.375. That is what mentioned in the previous table of binomial filter. So similarly, each filter value can be derived in different manners. Okay, so now we have this value, that is 0.0625 and 0.25, 0.375, 0.25, 0.0625. So multiply and divide everything by 16, we will get this value 1, 4, 6, 4 and 1. We are dividing with 16, so this is the final binomial kernel we can use for Gaussian purpose. Okay, so this image represents the Gaussian pyramid. So the right one represents analysis, and left one represents analysis and the right one represents resynthesis. Okay, so this is pyramid construction, this is reconstruction. In construction, what we are performing? Downsampling. Pyramid construction means higher image should be reduced. So on pyramid construction, we will perform downsampling. On pyramid reconstruction, we will perform upsampling. Okay, consider this. It is a original image with the larger dimensions. Okay, high dimensions. The binomial kernel is applied here. In this case, check that alternative pixels are omitted. So this is the layer 1, level 0 of pyramid. This is level 1 of pyramid. Here also the alternative pyramids are omitted, which means I am omitting every second pixel. So the factor I am going to consider is 2. Okay, so first one, second one is considered. First one omitted, second one is considered. First one omitted, second one is considered. Similarly, first one is omitted and second one is considered. First one is omitted, second one is considered. So this is pyramid construction. So the large level is reduced to smaller level. Next, we are going to reconstruct it. In order to reconstruct it, 3, 5 and the higher levels will be formed. This is level 2, level 1 and level 0. Okay, hope you are able to get it. So the darker pixels are the original values. Okay, so here the 3 will be the first one. This yellow circle is represents the white. This is insert the zeros. The white circle represents the, sorry, not yellow circle, the white circle indicates the zero values. The 3 is converted to 5 is converted to 7 or 9, so and so. Okay, So previously we have seen Gaussian one. Now we are going to see about the Laplacian pyramid. This is very important. The image may look big, but the operation is very simple. So the I is original image. I is original image. Yellow one are Gaussian pyramids. Blue ones are Laplacian pyramids. Okay. So the original image is converted into a Gaussian image first. Then the Gaussian image is converted to the Laplacian image. We have mentioned, right? Laplacian pyramid is derived only from the Gaussian pyramid. So how to get the Gaussian? First we have to blur and then we have to downsample. After getting the Gaussian image, we have to upsample and then we have to blur to get the original image. Okay, imagine that you have a image, you have applied a blur on it and you have compressed it or downsampled it. So now the image is blurred as well as it is reduced. That is the Gaussian image. Now we are going to reconstruct it to the original image. Means what we will do first, we will uncompress. That is, we will upsample the image and then we will reapply the blur or we will remove the blur, right, to get the original image. Now we have to check whether both the reconstructed one and the original one are same. That is the process mentioned here. So I have a original image. I have original image and I am blurring it, which means I have applied the interpolation. Sorry, I have applied the decimation low pass filter and I have downsampled. It produced the Gaussian image. The Gaussian image then is upsampled and interpolated. It will produce a blurred image. So original image and the blurred image is subtracted to produce the Laplacian images. So similarly for the second level, the same process is repeated. I am applying low pass filter and downsampling. I'll get the Gaussian one. And again, I am performing upsampling and I am applying the interpolation. It results in the some blur, and I am subtracting this with the original value, and I am getting the Laplacian image. So the right side of the image, first I am going to take the Gaussian one. If I have the Gaussian image, I have to perform only two steps, only upsampling and interpolation. So upsampling and interpolation provides the original image. This process will be repeated to produce a final image. And the intermediate Q represents quantization or some other pyramid processing. It can be used for any kind of noise removal. So simply we can say Gaussian alone produce a blur and Laplacian alone may lost the detail. So on combining Gaussian plus Laplacian, we can get the better results. So Gaussian means blur plus downsample, that is low pass plus downsample. Once we get the downsampled image, we have to upsample and then apply the interpolation, which is nothing but again a blur to produce the original image. We are going to subtract the predicted from the original to produce the Laplacian image. That is the combination of both blurred as well as, sorry, non-blurred as well as good detailed images. So the next one is, this is a normal, previously we have said this normal Laplacian transform. Now I am going to see the variant Laplace. Okay, variant Laplace means we no need to perform any upsample or downsample. We can blur directly using some other formula, and we have get the results of original by subtracting the blurred value. That is known as difference of Gaussians. Okay, we'll get the blurred image and we'll reconstruct it to get the original one. So this is the difference of Gaussian, which can't perfectly result in the reconstructions. So the next one is Laplacian of Gaussian. So I is nothing but image. We have to take an image and then blur with Gaussian. Okay. So take a image. Wait a minute. Yeah, take a image I and blur with Gaussian. Blur with Gaussian. Then apply the Laplacian second derivative. Okay. This is the formula. Okay. Take a image and then blur with Gaussian and then apply the Laplacian derivative. It can also be converted in different manner. So this LOG represents Laplacian of Gaussian, DOG represents difference of Gaussians. Both LOG and DOG can be used for edge reduction as well as block reductions. Okay, so we have three different types of representation: normal Laplacian pyramid, difference of Gaussians, as well as Laplacian of Gaussians. So depends on the application, we can use any type. Thank you.